Modern data centers consume nearly 2% of global electricity, much of it lost to heat in traditional copper interconnects. As bit rates exceed 100 gigabits per second per lane, electrical signals degrade over just a few centimeters of copper. We are moving toward a world where light travels through the silicon itself, using photons to replace electrical charge carriers. Photons do not interact with one another and lack mass, meaning they generate no heat through resistance during propagation. Silicon is opaque to visible light, but becomes transparent at near-infrared wavelengths, like 1550 nanometers. Silicon has a high refractive index of 3.45, while silicon dioxide is approximately 1.45. This high contrast allows for sub-micrometer optical waveguides that can be bent with small radii without significant loss. Silicon on insulator wafers serve as the platform, utilizing the top silicon layer for the optical circuit. Light enters the chip through grating couplers, which use periodic structures to diffract light from an external fiber into the waveguide. Alternatively, edge couplers use inverse tapers to match the mode size of a fiber to the nanometer scale silicon waveguide. Generating light within silicon is challenging because it is an indirect bandgap semiconductor, meaning energy is lost to heat instead of photons. To overcome this, researchers bond thin layers of indium phosphide onto the silicon wafer to create hybrid lasers.
These hybrid structures combine the efficient light emission of group 3-5 materials with the scalable manufacturing of silicon. Data is encoded onto the continuous light beam using a modulator, which changes the amplitude or phase of the wave. The Mach-Zehnder interferometer is a primary modulation tool, splitting light into two arms before recombining them. By changing the refractive index in one arm using the plasma dispersion effect, we can cause constructive or destructive interference. Applying a voltage changes the free carrier concentration in the silicon, which shifts the phase of the propagating light. This allows for rapid switching at speeds exceeding 50 gigahertz, translating electrical bits into optical pulses. Ring resonators provide a more compact alternative, consisting of a circular waveguide coupled to a straight bus waveguide. When the ring circumference is an integer multiple of the wavelength, the light enters the ring and disappears from the output. Tuning the ring resonance with a microheater or voltage allows for extremely energy-efficient modulation in a tiny footprint. Thermal stability is a major challenge, as the refractive index of silicon is highly sensitive to temperature fluctuations. Active feedback loops and specialized control circuits are necessary to keep ring resonators aligned with the laser wavelength. On the receiving end, we need to convert photons back into electrons using photodetectors. Pure silicon does not absorb near-infrared light, so we must epitaxially grow germanium on the silicon surface.
Germanium has a smaller band gap that efficiently absorbs photons at 1550 nanometers, creating electron-hole pairs. These carriers are swept away by an electric field to create a measurable current that represents the original data bit. One massive advantage of optics is wavelength division multiplexing, where multiple data streams share a single waveguide. Each stream uses a slightly different color of light, allowing for terabit per second throughput without increasing physical space. Arrayed waveguide gratings or cascaded ring filters can separate these colors at the destination with minimal crosstalk. Traditional electrical wires suffer from electromagnetic interference, where signals in adjacent wires bleed into each other. Photons do not carry charge and are immune to this interference, allowing for much denser routing of information. As chips become larger, the latency of electrical signals increases due to capacitive loading and resistance. Optical signals travel at approximately 2/3 the speed of light in vacuum, regardless of the distance on chip. Power consumption in electrical interconnects scales with the square of the data rate, creating a thermal ceiling. Optical interconnects exhibit a much flatter power profile, making them more efficient for long-distance and high-speed links. Silicon Photonics leverages existing complementary metal oxide semiconductor fabrication facilities, keeping costs relatively low. This allows the integration of millions of optical components alongside traditional electronic transistors on the same die. Monolithic integration puts electronics and optics on the same chip, minimizing parasitic capacitance between them. Electronic photonic design automation tools are evolving to handle the complex interplay of light and electricity in these circuits. Co-packaged optics involve placing the optical engine in the same package as a high-speed switch or processor. This reduces the distance the electrical signal must travel before being converted to light, further saving energy. Modern switches in data centers are shifting toward this architecture to handle the massive traffic from artificial intelligence workloads. Large-scale optical switch fabrics could eventually replace electronic routers, directing light beams with micromirrors or phase shifters. This could reduce the need for constant optical to electrical conversions, which are a major source of energy loss. Optical computing is a related field where light is used to perform mathematical operations like matrix multiplication. By using Mach-Zehnder mesh networks, we can perform linear algebra calculations at the speed of light with very low power. These photonic tensor cores are particularly promising for accelerating neural network training and inference. Integration challenges remain, such as the high precision required for fiber-to-chip alignment during packaging. Laser sources also degrade over time and are sensitive to the high operating temperatures inside a processor package. External laser sources are often used to move the heat load away from the sensitive compute chip. Polarization management is another hurdle, as silicon waveguides are typically very sensitive to the orientation of the light wave.
Polarization rotators and splitters are integrated to ensure the system works correctly with standard optical fibers. Future developments aim to use nonlinear optical effects for signal processing directly within the silicon. This includes four-wave mixing and the Kerr effect, which can enable all optical logic gates. The transition from copper to optics is not just an upgrade, but a major shift in computer architecture. We are moving toward disaggregated data centers, where memory and processors are linked by optical fabrics rather than buses. This allows for much more flexible resource allocation and massive improvements in overall system efficiency. Silicon photonics bridges the gap between the speed of light and the logic of silicon transistors. The density of integration continues to double, following a trend similar to Moore's law for electronics. Within a decade, the wires inside your laptop could be replaced by nanoscopic beams of infrared light.